Welcome back to Science Unpacked. Today, we're diving into some fascinating chemistry, looking at a paper about new catalysts.
Oh, catalysts. Always exciting. What kind of catalysts are we talking about today? And what do they do?
Well, the paper is titled Catalytic Potential of Pyrazolone based Dioxidomolybdenum VI complexes for multi-component Biginelli reactions, epoxidation of olefins, and oxidative bromination of phenol derivatives.
Whoa, that's a mouthful. Can you break down those big words for us? Especially pyrazolone and dioxidomolybdenum.
Absolutely. Pyrazolones are organic molecules often used in medicines. Dioxidomolybdenum VI refers to a specific type of molybdenum compound, a metal, where molybdenum is in a high oxidation state with two oxygen atoms attached.
So, they're combining these organic pyrazolones with molybdenum metal. Why is that combination interesting for catalysis?
Pyrazolones act as ligands, basically chemical anchors, that bind to the molybdenum. This creates a stable complex that can then facilitate chemical reactions.
Ah, so the pyrazolone helps the molybdenum do its job. What kind of job specifically did these new complexes perform?
The researchers explored three main catalytic applications. The first was the Biginelli reaction, which is a way to make complex organic molecules.
The Biginelli reaction. I've heard of that. It's important for creating special compounds, isn't it?
Yes, it creates three FOUR, DIHYDROPYRIMIDIN, 21H1s and thiones, or DHPMS. These are biologically active molecules found in many pharmaceuticals.
So these molybdenum catalysts are helping synthesize potential drug components? That's really cool.
Exactly. And they found that these reactions worked really well, even under solvent free conditions, which is a big plus for environmental reasons.
Solvent-free chemistry is fantastic. Did they use hydrogen peroxide, H2O2, in these Biginelli reactions?
They did. H2O2 actually improved the yield for the one type of DHPM, but surprisingly, it acted as a poison for the thione type.
That's a tricky balance. So they had to adjust their approach depending on the specific DHPM they wanted to make.
Precisely. They optimized the process to get good yields for both types, even without H2O2 for the thiones, which is quite clever.
Okay, so that's the Biginelli reaction. What was the second exciting application for these catalysts?
The second was the epoxidation of olefins. This is a process where you add an oxygen atom across a carbon-carbon double bond, forming an epoxide.
Epoxides are super important in industry, right? For making plastics, resins, and other chemicals.
You got it. The molybdenum complexes were very effective, converting various olefins into their corresponding epoxides with high selectivity.
Did they need H2O2 for this reaction too? Or was it different?
Yes, H2O2 was used as an oxidant and sodium bicarbonate as a promoter. These were crucial for achieving high conversion rates and selectivity.
Fascinating factorial. And the third application, oxidative bromination of phenol derivatives, sounds quite specific.
It is factorial they successfully added bromine atoms to phenol derivatives like thymol, creating new brominated compounds.
Isn't that similar to how some natural enzymes like haloperoxidases work in biological systems?
Exactly. It mimics that natural process. They found high selectivity for specific brominated products, such as for BROMOTHYMOL, which is impressive.
So, these molybdenum complexes are incredibly versatile, capable of driving multiple important chemical transformations.
And there's more. The catalyst showed good recyclability, meaning they could be reused for several reaction cycles without significant loss of activity.
Recyclability is a huge advantage for industrial processes, making them more sustainable and cost effective. That's excellent.
They also used computational studies, like DFT, to understand the reaction mechanisms, showing how these catalysts actually work at a molecular level.
That's the full package then. New catalysts, multiple applications, green chemistry aspects, and a deep understanding of their function.
Indeed, this research really showcases how smart design of metal complexes can lead to efficient and versatile tools for chemical synthesis, with broad implications.
It's truly inspiring to see how fundamental chemistry can pave the way for new medicines and industrial processes. What a great paper!